Hello. In this video, I'm going to introduce a new class of function called hyperbolic function. As a short motivation, we're going to take a little detour into complex numbers, which is something that you have encountered before. Um, these are numbers of the form a plus ib, where I is square root of negative 1. There's a very famous relation that arises in the study of complex numbers, and that's given by e to the power I theta is cosine theta plus I sine theta. It's a very beautiful result. Now, let's take this as given because we don't want to delve into how we get this result or what this result means. But there is a way we can motivate the topic of hyperbolic function using this. If I were to find e to the negative I theta, that would be cosine negative theta plus I sine negative theta, giving me cosine theta minus I sine theta. And then I also have e to the I theta is cosine theta plus I sine theta. If I add these up, the sine theta part gets cancelled and I end up with cosine theta equals e to the negative I theta plus e to the I theta over 2. Similarly, if I subtract, the cosine part gets cancelled and I'm left with sine theta equals e to the I theta minus e to the I negative theta over 2i. Now we already know that sine and cosine are trigonometric functions that have very nice integrate relationship with each other. And what we observe here that sine and cosine can also be written as functions of the form e to the negative box plus e to the box over 2 and e to the box minus e to the negative box over 2. But I'm using the box to indicate that it's some variable or it's a function of this form. And so it seems like these functions should also have properties analogous to the trig ratio. And it turns out they do. So we define these functions as you can sine h of x, or you can read it as sine x is e to the x minus e to the negative x over 2. And we define cos x or cos hx as our hyperbolic cosine x as e to the x plus e to the negative x over 2. And in a manner consistent with trig ratios, we define tan hx as sin x over cos x. In fact, other properties of that we're familiar from trigonometry also follows in hyperbolic case. Now, the reason these functions are called hyperbolic functions is because they arise from hyperbolas in a similar way that trig ratios arise from circle. Recall that if I take a circle and I pick any point at an angle theta from the x-axis, the coordinates of that point are given by cosine theta and sine theta. Similarly, if I have a hyperbola and I pick a point, the coordinates of that point are given by cos x and sin x, except in this case x does not represent the angle, but it actually represents the area of the shaded region. So there is some physical relationship with the hyperbolic function. What do these functions look like on the graph? It's actually easy to draw the graph because they are kind of averages for e to the x and e to the negative x. So this is an added average. So that's where cosine x sine lies. For sine x, it's the average of or the sum of half e to the x and negative half e to the negative x, which gives me this purple graph for sine x. You can try and figure out the graph for tan h of x as an exercise. Let's find derivatives of this function. We know the definition of sin x is e to the x over 2 minus e to the negative x over 2. Taking derivative gives me cosine x, which is a relation similar to trig function. Now all of these relations work in the same way with a modification in sign, meaning derivative of sin hx is cosine hx, derivative of cosine hx is sin hx and not negative sin hx. Derivative of tan hx is secant h squared x, and then so on. You can refer the book for the remaining three, or if you want a more hands-on practice, you can try to derive the derivatives of secant hx, cosecant hx, and cotangent hx. Now, since we have looked at the hyperbolic function, Obviously, we also want to look at inverse hyperbolic function. Now, the hyperbolic functions are defined with exponents. Not, so the inverse are going to be defined with logarithms. And that's because, well, logs are the inverses of exponential. So sine h inverse of x is log of x plus root of x squared plus 1. Cosine h inverse of x is log of x plus root x squared minus 1. And tan h inverse of x is 1 half log of 1 plus x over 1 minus x. A very useful and important exercise would be to get this relationship from the formula for sine hx, cosine hx and tan hx. I'm going to derive the one of them for you, and then I'm going to leave you to do the remaining two as practice. Let y equal sine h inverse of x, means x is sine h of y, which is e to the y minus e to the negative y over 2, or 2x is e to the y minus 1 over e to the y. Now multiplying throughout by e to the y, I get e to the 2y minus 2x e to the y minus 1 is 0, which becomes e to the y squared using properties of exponent minus 2x ey minus 1 equals 0. Now you will recall that this is a quadratic-like equation that you did in Math 103, and it's a quadratic in e to the y, which means e to the y equals, by the quadratic formula, 2x plus minus square root of 4x squared plus 4 over 2, which gives me e to the y equals x plus minus root x squared plus 1. Now we discard the negative. Why do we discard this? Well, if you look at x squared plus 1, that's always going to be more than x, which means the square root of this thing is always more than x, so this number is always negative. But e to the anything can never be negative, so we discard the negative value, which gives me that y is ln of x plus square root of x squared plus 1 as required. Now at this point, you can derive, and I would highly recommend you to derive the expressions for cosine h inverse and tan h inverse using this as a reference point. What about derivatives of the inverse function? Now again, we can follow the same exact process we did for inverse trig functions, which is let y equal sine h inverse x. So h is x is sine h y. Taking derivative gives me 1 equals cosine h y times dy over dx, or dy over dx is 1 over cosine h y. From the identity, I get 1 over square root of 1 plus x squared. The only difference being that over here the identity is cosine h squared minus sine h squared x is 1. And that's because it lies on a hyperbola whose equation is x squared minus y squared is 1. Now, concept check. Instead of using this definition of sine h inverse, if you use the log definition of sine h inverse, can you show the same result? You should get that the derivative of the log form of sine h inverse x, should also give you 1 over square root of 1 plus x squared. The other derivatives of inverses are as follows. A practice exercise would be to try and derive these relations from scratch. You can either use the method I showed here, or you can use the log definitions in order to find the derivatives. So that's the end of the material. Here's worksheet 2. The first problem is calculate the integrals. These are indefinite integrals. Using logarithmic differentiation, find dy over dx if this relationship is given between x and y. These two problems are from the textbook, which you can find from on your WebAssign link. Like when you log in for WebAssign, there's an e-text option there. Sketch a graph. Use the tools that you remember from Calc 1 for sketching graphs. Find the derivative for these inverse function. Prove this identity. Hint is there's a similar problem which is covered in the lecture. You can use a similar method. Let this function be given to you. You have to find if x is continuous, if f is differentiable. Recall the definition of continuity, finding left-hand limit, right-hand limit, and the definition of differentiability, where left-hand derivative, right-hand derivatives need to exist. Prove these two identities for hyperbolic function. And lastly, at what point does this curve have a tangent? Does a tangent have a slope of 1? So that's it for material